So last video we ended with finding the correct equation to use for the scenario here. And so we're solving for x final. Let's look at this and see if there's any zero components for us. X initial is 0, and then velocity final is 0. Okay, I'm going to minus velocity initial to the other side because it's added to what I'm solving for. So I could rewrite this as negative velocity initial squared is equal to 2 multiplied by the acceleration multiplied by x final. And then the last part of this, I'm going to divide my 2 and my acceleration to get x final by itself. So x final is equal to negative velocity initial squared divided by 2 times by acceleration. And now let's just plug in those values. We know that velocity initial is 22, so we have a negative 22.5 meters per second, and that's going to be squared. And we're going to divide that by 2 multiplied by negative 9.81 meters per second squared. And so this is great, right? This realization, this understanding that I have a negative and it's going to cancel out this negative. And how having that will give me a positive x final, and that should make sense because we chose our origin to be down here, and we're saying going in this direction is positive, so our x final should be a positive number. Let me grab my calculator. Okay, so I'm going to take that negative, well, so the 22.5, because this negative is outside of this 2, so you should keep that in mind. Okay, so 22.5 squared, and then the negative of that, and then 2 multiplied by my negative 9.81. This final is 3 sig figs, 3 sig figs, so 25.8 meters. How long will the ball remain in the air? So now we're looking for what is time final. You can take that info and you can plug it in there. It can be part of your list now. So we need to pick an equation that we're solving for time final with. And velocity final is a 0 component. Time initial is 0. Now, this is a simple equation, and I'm going to choose to use that one because of its simplicity. I want you to notice, like, you could have chosen this or this one. This one's going to be hard to solve for because our time finals there, they're separated and we'd have to bring them together. So I'm going to use that one. Velocity final equals velocity initial plus acceleration multiplied by time final. I'm solving for time final. So I'm going to first subtract velocity initial from both sides. Okay. And now I'm going to divide by acceleration to get it by itself. So velocity final minus velocity initial divided by acceleration. I'm going to plug in those numbers. So my final velocity was 0. How long will the ball remain in the air? We're going to double it. We're going to see, well, let me think through this. Let's figure out how long it's going to take for it to go from here to there, and that's kind of how we have this problem set up. So velocity final is 0. Velocity initial, 22.5 meters per second. Acceleration, negative 9.81 meters per second squared. So negative 22.5 divided by 9.81, negative 9.81. So that would give us 3 sig figs, 3 sig figs. We have 2.29 seconds to get from here to there. Okay. All right. As the ball travels, what is the acceleration on the ball at the top of its flight? The acceleration is the same throughout. There's only, as soon as this ball is released, there's only one force acting on it, and the only force is the force due to gravity, so its acceleration is due to gravity. So the acceleration throughout the whole arc is negative 9.81 meters per second squared. And then, does the acceleration ever change? We talked about that. No, it doesn't. Because the force acting on it didn't change, and so the acceleration can't change. All right, weight and force. When we talk about weight, what are we really referring to? We're referring to the force due to gravity. When we measure mass, why do we weigh it? Well, we weigh it because we're on Earth, and so we can have that constant force, that constant acceleration due to gravity, and so we can figure out the mass quite easily, meaning the force is the force due to gravity, whatever that might be. And then we have mass, so we want to know what the actual mass of the object is, and then acceleration, which will be a negative 9.81 meters per second squared. And so scales read this, and so then they simply divide and tell us what the mass is. But this is only true for here on Earth. If we went somewhere else, that wouldn't be the case. So are mass and weight the same thing? No, they're not. Weight is a force, the force of gravity that the object is applying, or is being applied to the object, I should say. And then mass is not a force, has units of kilograms, and that's about the amount of matter contained within that object. And so we just talked about how they're different. Okay. So, observe the ball to the left, free fall through the air. If we neglect air resistance, what forces are acting on the ball? Only the force of gravity is acting on the ball as it's falling through the air. So what is our net force? Well, it would only be gravity, because if we add all our forces together and that's the only force, then our force net is going to equal the force due to gravity. What is the ball's acceleration? It's the acceleration due to gravity, which is negative 9.81 meters per second squared. Okay. So, a bathroom scale contains springs. When you step on the scale, you exert an upward force, it exerts an upward force on you because you're in contact with the scale, right? Like a normal force, but in this case, it's the springs that are pushing back up on you. So because our net force is equal to 0, the springs must be exerting an equal and opposite force to the force due to gravity, or your weight. So that spring force is going to equal the force due to gravity. Okay, and let's think through that. So here's my free body diagram. For this gentleman, we have the force due to gravity, but he's stationary, so the net force is 0, and this force due to gravity is actually canceled out by this spring force, and so they must equal one another as far as magnitude goes. So the magnitude of the spring force is your weight, and that's how scales work. Okay. So how do we measure mass using a scale? We kind of talked about that before, how on Earth our acceleration is due to gravity is always going to be negative 9.81. And so we can, that spring force is the same as the force due to gravity, and then from this component and that component that's constant, we're able to figure out what the mass of the object is. Suppose you're standing in an elevator that is accelerating upwards, okay? And notice, we said acceleration, so that means that there's a net force, that they're not equal. It's not in equilibrium. Is the magnitude of the normal force exerted on you by the floor, the magnitude of the normal force exerted on you by the floor of the elevator the same, larger than, or smaller than the magnitude of your weight? So if I'm standing in the floor of an elevator, on the floor of an elevator, I have my force due to gravity, okay? And then I have the elevator floor pushing back up on me. Okay, so force normal. But this normal force has to be greater than the force due to gravity because there's an acceleration involved. And we want that acceleration to be in the positive direction, so that's why that one's greater. So with the elevator stopped, what will the scale read? Well, the scale will read your weight, okay? Because it's programmed based off of the acceleration due to gravity of Earth. Okay, so you stood on the scale in the elevator, accelerating upward. What would be the weight displayed on the scale? Well, do you see how when it was accelerating upward, so that normal force of the scale pushing back up on us is greater, and that's what the scale uses to read mass or weight. So it would be incorrect. It would incorrectly read a greater mass. And so it's just saying that the force being pushed up, the scale pushing up on the person while the elevator is accelerating upwards, is actually greater than the force due to gravity. So what is the system? Well, the system in this case is the person. And so what forces are exerted on you? Force due to gravity, and that spring force of the scale, or the normal force. We drew a free body diagram of this. What direction is the net force? The net force is up because we're accelerating upwards. What happens to the overall magnitude of the reading on the scale? It would increase. Suppose the elevator were instead accelerating down. Predict what would happen to the reading on the scale. So now we're no longer accelerating upwards, we're accelerating going down. So what do you think would happen there? It would change. We have our force due to gravity, right? That's the same. But our acceleration is in the negative, so our net force is in the negative. And so now this normal force, or the spring force, is actually less than our force due to gravity. And so what would happen to that reading? Well, now it's smaller than our force due to gravity, so the scale is actually reading a value that is less than the actual mass of the object. Okay, so let's just take a moment to look at this. Let me check the time. We're going to wrap up with the next video, looking at this and talking through it. It's this exact same concept as before, and then we're done with learning target number 2.